let's hear it for the world-class NASA STEM Stars team. From NASA centers across the country, we present Dominic Lundy. Hello, my name is David Alexander, connecting to you from the Armstrong Flight Research Center. And welcome to NASA STEM Stars, where students connect firsthand with NASA scientists, engineers, and innovators to learn more about their missions, career paths, and opportunities. As you may know, the engineering design process is an iterative process that engineers use to guide them through problem solving. NASA engineers ask questions. They imagine solutions, they plan designs, create and test models, and then make improvements based on these models. These steps all contribute to mission success here at the agency. Today, we're going to focus on the testing phase in the engineering design process. Green Run is a series of tests during which test engineers will actually test the Space Launch System, or SLS core stage, before actual launch in the future. In today's mission, we're going to meet the person who is in charge of firing the RS-25 engines. Joining us today is Dominic Lundy from Aerojet Rocketdyne. He is an actual aerospace engineer. He engineers the lead for model-based systems, engineering, and transient analysis. So we welcome you to the program today.
Thanks, David.
Awesome. Dominic is actually going to share a little bit about his background, his career experiences, and the work Rocketdyne does for NASA. So as you're listening to him share his story, we really want for you to come up with some questions to ask him. So about half of our time is going to be devoted to answering your questions. So please enter those questions in the chat throughout the conversation today, and we'll actually try and answer them before we wrap up for today. With that said, I'll turn it over to you, Dominic, to get us started.
Thanks, David. Hi, everyone. My name is Dominic Lundy, like David said, and I'm an aerospace engineer. So I work at Aerojet Rocketdyne as a system performance analyst. And I want to tell you a little bit about myself. So I went to California Lutheran University for my undergraduate. I did a physics bachelor's of science there. After I finished that, I went over to Cal Poly San Luis Obispo up in beautiful Central California. I did my master's in aerospace engineering there and just finished about a year ago.
Awesome. You have a really phenomenal education, Dominic. Do you have any time for yourself? What do you do in your free time?
I do have free time. Yes, I'm able to do a lot of fun things. One thing I really enjoy is to go rock climbing. So I'll go out and I go to the gym and practice my rock climbing. Recently, I think last summer, I got to go climb this hill above Mammoth. That was more of a mountain than a hill. I really am into road biking around the cities and mountain biking in the hills. And recently, in quarantine, I've gotten into disc golf, which is where you throw your little frisbees into baskets and try and keep a low score. I also like to do things inside. I like to do coding. I'm really adamant about coding. When I was 12, I saved up all of my money from Christmas, told everyone just to give me money, and I went and I bought a Lego Mindstorms. And I got to build Legos, then I got to put sensors on them and code them to do the things I want to do, like pick up a ball or follow a line. It was really special. I also am just really into space exploration in general, and I like teaching as well. I've taught a few classes, and I'm looking forward to some more teaching opportunities.
That is really awesome. You have a whole plethora of experiences all together. I've been to Mammoth. I've been snowboarding there. Are there any other mountains you like to climb out there?
Out in Mammoth, if you go a little bit north to Yosemite, I did some of my first rock climbing there, and I also got to watch my cousin climb El Capitan, which was unbelievable to watch. It's like a 7-day climb for him. It was special.
Wow, that is totally amazing. Sounds like the triathlons of mountain climbing all together. If you add swimming, you'll definitely be finding yourself to doing that.
There
Speaking
you
of
go.
which, do you do any of your interests like I know you mentioned coding, for example. Do any of your interests
Hmm.
coincide with your career?
Yeah, so I would say like coding, like you said, in space exploration, but coding really is what led me to where I am today. As an analyst, we spend a lot of time looking at lots and lots of data. And so we code different ways to process that data. We also create models of the system. So we say, if we turn this valve, what will happen? And so I code those things. And that coding has come from all the way back when I was doing Mindstorms, through high school, through college, through my master's. It's been following me the whole way.
Hmm. You have an extensive array of experience, and I really love that. But for our listeners that are out there, how did you get to where you are today in aerospace?
Yeah, so I think I went through a lot of different projects to get to where I was, and I wanted to show you a couple here on the screen. On the left, you can see a project I did for summer research at Cal Lutheran. I got to code a model of a superconductor. A superconductor is this really incredible material that we like in physics, where if you bring it down super cold, I'm talking like if you touch it, you will burn your fingers because it's so cold, burn them because it's so cold. If you bring it down that low, it has complete 100% efficiency. It is perfectly solid. And it's really cool to watch the models work. So I did a whole project on that one summer and presented in front of a couple research groups. And then on the right, you can see Dawn. That's my solar car that I got to build at Cal Poly's Prove Lab. If you see over there, I am the guy in the orange vest taking care of the car. It's a solar car. So what that means is we take the sun's rays, we put them on top of the car, it turns it into electricity, which turns it right into an electric motor to make us go down a runway at 65 miles an hour. Well, almost 65. We
Wow.
haven't hit it yet. Yeah, that was
That
really cool. I got to be the test
yeah,
lead, which means I was in charge of writing all the test procedures and I was in charge of managing all the people, making sure we kept our driver safe.
okay, that's really neat. So I have a question here from a student. Student wants to basically know, at what point in your life did you realize that you wanted to be an aerospace engineer? But at the same time, I think in answering that question, you should probably also discuss a little bit more about what an aerospace engineer is.
That's a really good question. Okay, I will start with what an aerospace engineer is to me. I think to say it pretty simply, an aerospace engineer is somebody who helps to build rockets and planes. And how I got there was I actually have a very defining moment. I was doing physics for my undergraduate, which is a little bit different than aerospace engineering. And I was doing a project at William and Mary in Williamsburg, Virginia. And I remember doing this project and saying, I want to work on something where I get to build it and make like a difference for people. And so now at my wall at Aerojet Rocketdyne, I have a astronaut wall of all the astronauts who I've met, who I've gotten their signatures or shaken their hands, and of all the people who will fly on the rockets that I build.
That is very inspiring. So let's talk a little bit more about the rockets that you make. You're currently working on the Space Launch System. So, for our viewers who are not so familiar with this, what is the SLS and what is it going to do for us?
The SLS is an amazing rocket. I'm so excited to work on the Space Launch System. So this is the rocket that is going to bring us to the moon and to Mars, which is just so exciting to think about, going to
Hmm.
another planet. It's insane. I get to work on the engines on this rocket. Let me show you a little bit about what this rocket's all about. On the white there on the side, those are the solid rocket boosters. Those produce a ton of force really fast. They produce both of them together around 6 million pounds of force. In the top, the very top, there's a little white part. That is the Orion spacecraft. That's where we're going to be putting humans, actual humans, on top of this rocket to launch them to the moon and to Mars. And then we've got the core stage, which is the middle orange part, which holds all of our fuel. And then right below the core stage is my RS-25, my four RS-25 engines. And this rocket's going to launch the next woman, and the first woman and the next man to the moon by 2024. And I'm so excited to work on it.
Yeah, that is very, very important work that you do all together. And just as important, in terms of motivating our next generation of explorers. And we have a question from a student here, and the student is basically asking, what advice would you give to a student who wants to get into aerospace?
That is a really good question. Um, I think I got a couple things. I know that I didn't know if I wanted to be in STEM when I was younger. But I know that while I was in school, I really paid attention to each and every math class because I knew each math class built off each other. So I knew I had to pay attention there, and every science class built off it. Also, like learning how to work on team projects at school was really important to me. But when I was younger, I didn't think about all that. All I could think about was how much fun science was and how much fun I had playing with it. I remember building tons and tons of baking soda and vinegar volcanoes in my backyard, blowing up balloons using the bottles, or taking a balloon on a string, launching it. I had this whole paper airplane book, and I think I went through every single one, understanding how they work. So for me to get into a career in STEM, just don't be scared of being a little nerdy or a little bit excited about science things. It's really fun stuff, and like get your friends involved and go play with things that like most other people don't play with. Maybe like trying to figure out how you can bounce a tennis ball on top of a basketball and see how high it goes and figure out why that happens.
Yeah, you definitely have the opportunity to do big things at the National Aeronautics and Space Administration. It's my little testament to the student that asked that question. But speaking of size and sizable goals and things like that, how big is the Space Launch System?
Oh, it is massive. It is humongous. I think we have a little graphic to show you, but it is 322 feet tall, which is larger than a football field, which is insane to think about. So a normal human is about 6 feet tall, and so take 6 feet, and we are only as big as the engines at the very bottom of that picture. If we can see here, only a tiny bit.
Mhm.
Um, this rocket is so big it can launch us at 24,000 miles an hour. It's going to get us to the moon, which is over 200,000 miles away. Numbers that are just insane to think about. Riding a rocket for
Mhm.
200,000 miles. That's a really long road trip. I would be asking, are we there yet? And it only takes like 2 days, but that's a good amount of time.
Yeah, definitely. Now, we have the Saturn, which essentially took us to the moon. We also
Yep.
have the space shuttle. So,
Yeah.
question here is that how new are the capabilities of this particular rocket compared to those other technologies?
Yeah, so I'm really excited to be working on the SLS because of where we are. We learned how to build big, large moon rockets with the Saturn V, but it had to be very, very large, and it didn't have a ton of extra capability because it was using less efficient engines and older technology. Then we went on to the space shuttle where we built the International Space Station. We worked on the Hubble spacecraft. It's a plane that can fly into space and land on its own. It was amazing. And
Hmm.
the engines on it, the engines I work on, called the RS-25 engines, those are the most efficient stage combustion engines that fly today. They're also our most experienced of any rocket that we have, any large stage combustion rocket that we have in the United States. It's a rocket that has over 1 million seconds of testing time. And we know this rocket, like our team knows this rocket inside and out. We know how these engines work. So I'm really excited to be working on the SLS, which is taking the moon rocket type build where you have the people on the very top and a very large multi-stage rocket. But on the bottom, you've got very high efficiency engines, large solid boosters that we know work really well, making it a really reliable but also super powerful rocket all at the same time.
Okay. So I'm really excited about the SLS, especially the way you talk about it. I'm totally excited. Is this capability going to fly like next week or?
I wish it's coming up really soon. So right now we actually have built the first core stage. That's the orange tank. We have that core stage built, and we have our four RS-25 engines bolted onto the back of it or attached onto the back of it, and we have that whole core stage up in the Stennis Space Center's B2 stand. So the B2 stand is in Mississippi at the Space Center, and it's going to hold down the entire stage as we turn on the rockets. So what we do is we're going to fill up the propellants in the whole core stage. We're going to practice cooling down those liquid hydrogen and liquid oxygen to these cryogenic temperatures, which means they are freezing cold. And then we're going to turn on all the computers and then turn on all the engines and make sure the entire thing works correctly. Once we do that, we're going to go ahead and take our core stage and we're going to ship it over to Kennedy Space Center in Florida. We're going to attach on the solid boosters, attach on the exploration upper stage, attach on the Orion, and off it goes to the moon.
Now, you talked a lot about igniting propellants. You talked a lot about hardware and the fact that computers are going to play an integral role with respect to the Space Launch System. Student online has a question here which coincides and relates to the things that you were basically saying. So as a more specific question, what advice would you give to students here when it comes to the different paths or the different specialties inside of aerospace engineering?
That is a really good question. I like that one. So aerospace engineering, at least at Cal Poly where I went, was split between astronautics and aeronautics. So the astronautics students would learn how to build rockets, and the aeronautics students would learn how to build planes. Now, for the first, so throughout high school, even if you know you're going to be an aerospace engineer, your classes are the same. For the first 2 years of undergraduate, even if you know which type of rockets or planes you want to build on, classes are the same. So your decision only really comes towards the middle of your college career. And that's where you start learning. If you're aeronautics, you start learning about wings. You start working in the wind tunnel. You start practicing figuring out what is supersonic flow and that kind of stuff. And then if you're an astronautics kid, you start learning about orbits. You start learning about electric propulsion. How to decide between the two? It's really just being exposed. It's really just saying, what kind of stuff do I want to work on? Do I like working with rockets, which are larger but don't fly as often? And do I want to work with planes, which are much more of a production? We make lots and lots of them, but they don't go as fast as rockets do.
Okay, excellent answer on this end. So the Space Launch System is a very big project. It has a lot of moving parts. You spoke a lot about the differentiations with respect to aerospace engineering, but what do you actually work on specifically?
So I get a really cool job. My job is called Transient Analysis, and it's my job to turn on the engine. So it's my job to figure out how to get the fuel propellant into the engine at just the right rate and turn them and light them on fire just the right way so that nothing breaks and the engine turns on every time. It's really exciting work. But I don't get to play with the knobs. I'm not in the test center going, we're going to turn it on now, because we turn it on in under 5 seconds. I am not that quick. I am not speedy like that. So what I do is I do a lot of modeling and analysis, really detailed analysis work to understand exactly how all of the parts of the engine are going to work when we try to turn it on. And then it's my job to tell the computer exactly how to turn it on. Tell the computer to turn this knob, then turn that knob, then turn this knob, then turn that knob backwards in order to turn on this engine reliably, safely, over and over again for our testing purposes.
Okay, excellent. Now, earlier in the program, I spoke a little bit about the engineering design process and why testing is such an important element to the engineering design process. So why are the green run tests so important? And how many times do we actually test?
Yeah, so I'll bring it back to actually when I was building my solar car. We were a lot smaller project, only 30, 40 people. And testing was so important. It's the most important thing for us. We would get out to the field and we would test and immediately find out something very important about the project that we had to fix. If we had gone for the record that day, we would have never completed it. We wouldn't have gotten the car turned on. Through testing, you find all of the little details. You find all the variations that your brain can't think about, even the best we try. Now, when we are testing the SLS, we might find things. We're hoping to be able to test the whole system, really figure out how to work with it, how to turn it on efficiently, how to work with moving this massive stage around. So
Mm-hmm.
every single component on the entire SLS is tested by itself. Then it's put together. So every component of my engine is tested on its own. Then we put the engine hull together and we test the engine in what's called an acceptance test. We turn the whole engine on. We run through all the checkouts. Then the core stage is going to be our full test. So we test every part as it comes in each and every time, and then we test the entire thing to make sure it's going to work perfectly, which I am 100% expecting it to.
Mm-hmm. And I know in terms of your position and everything that you aid in terms of igniting and starting the vehicle or the core stage at least during the green run test, that is. But we're talking about this marriage between hardware and software. Can you just talk a little bit more about what is the role of software engineering at NASA? We had a student ask that question.
Yeah, that's a really good question. So, software engineering is really, really, really important right now. There are so many things that are so complicated on a rocket that you cannot do manually. There's no way we have time for the Orion astronauts to be able to do things that a computer could. And even if they did, they couldn't. All they would be able to do is tell a computer to do it, because every single engine is called gimbaling. So every engine can move back and forward and backwards. Even the solid boosters on the side, they have thrust vectoring on them. This enables us to turn the rocket. There's no way a human could pull, like the old planes when we started building planes. You had a lever that you would pull to move your wings, to move your wing surfaces. You can't do that with this. We have complicated hydraulics, kind of like excavator type machines that move the engines back and forth while we're flying. So software engineering is really, really important. It's also really important because you're flying humans on top of it, and it's very easy to. There's a lot of complicated things going on, and so you need to manage all of those things in the software. Software engineering is actually pretty critical for SLS.
Wow, that's terrific. So let's just digress here for a moment on this end. You're talking about the people, the team spirit behind the operations. We're talking about the management. How important is teamwork in your job with respect to aerospace?
Well, it is so important. For me, it's one of the most important things. Everyone, when they are talking about like Aerojet Rocketdyne or NASA, they always talk about the people they're working with. Everyone who says, if you ever ask anybody, do you like your job? They always say, I love my job and I love the people I work with. It's so important just because we're made to be people who work. Like, one reason is because we like to work with people. But secondly, no one can build a rocket like this by themselves. There's no way. It's impossible. No one can even build an engine, let alone even some of the parts of the engine by themselves. There's not a single person who knows everything. You have to work in a team in order to complete an amazing cast like this. And so that's where you really learn. Like when I was in college, I had a thesis team. So I had 3 different people on my team that I had to work together with, 3 different advisors. When we worked on wind tunnel projects or when we worked on projects for smaller companies, we got to work on specialized teams, spending all of our time together, learning how to communicate effectively, how to share responsibilities, how to get over disagreements and figure out what the best path going forward really is. Teamwork is one of the most important things in my book, especially when it comes to aerospace engineering.
Absolutely. And you're talking about the love for technology and the love for people, which is very important. Speaking of which, in terms of people, who are your role models? Who had an impact in terms of you and your life?
So I have a lot of important role models in my life that I can think back on. Just a few of them. Let's see. My high school teacher in calculus, Mr. Stebbins, he was really instrumental in getting me excited about the math that was really hard. He was really excited about it, and he was really good teaching, making sure we worked hard, but really was able to learn and weren't too confused by ourselves. My advisor in undergraduate for physics was Dr. Deitz, and he taught me a lot about the power of communication. He taught me a lot about the power of hard work. He taught me a lot about how to teach. I had an advisor in my master's program called Dr. Amelia Gregg. She was also really amazing. She helped me get to have the confidence to go work in Japan for a whole quarter and work on satellites in Japan, in a country I don't know how to speak the language. She had taught me the confidence to complete my thesis, 140 pages, and she really inspired me to be a good aerospace engineer. And then my dad and grandpa, they're always good inspirations as well.
That is awesome. Now, we talk about NASA, which stands for the National Aeronautics and Space Administration. Question here from a student: is aerospace engineering the same as aeronautics?
So aeronautics is a part of aerospace engineering. So some aerospace engineers do aeronautics. And aeronautics is really just figuring out how wind flows is the easiest way to think about it. It's fluid flow over items. So aeronautics engineers include figuring out how to build wings, figuring out how to build the shape of the rocket, figuring out how to work on turbine blades, which are moving through gas. That's what aeronautics engineers get to do.
Okay, great. Another student had a question with respect to actually becoming an astronaut. They asked, well, are there any specific degrees needed to become an astronaut?
So I think it's highly recommended that you have a degree in STEM. That's at least my understanding. And it's very important that you show that you know how to work in a team, that you show that you know how to work hard, and that you show you know how to learn. Astronauts that I've met are like the most humble people. For us, they're like superstars. And for them, they're coming down to my job and they're talking to me saying, what do you do and how do you do it? And I'm like, the astronaut wants to know what I do? This doesn't make sense. But they know how important everyone's job is. And they are kind of the unofficial leaders of our teams, or at least the unofficial mascots of our teams, because we're doing all of this for them. We're doing all of this work to keep them safe and healthy and get them to space. And I think they understand that and they know how important that is to them.
Yeah, absolutely. I totally understand with respect to that, and looking up to many of the women and men who are astronauts and who actually put their lives on the line in the name of science. So here for a moment before we run out of time on this end, can you tell us about maybe a career challenge that you may had to overcome to where you are today?
Yeah. So I would say one of the biggest recent challenges I had was my master's thesis. So when you graduate undergraduate, sometimes you go and do what's called a master's program. And that master's program, a lot of times you have to write a paper. So you do a project and then you write a paper about that project. And then you take that paper and you send it off to experts and they come to you and they review it. So you have to defend it. So you have to stand in front of a room and say, I did this correctly and I know what I'm doing and I made significant advances. I don't like writing. I don't enjoy writing. It is not the thing I do. I would rather be put in front of a computer and code all day. I actually coded my writing part of my thesis because of how much I like coding. So writing cool. 140 pages took a lot. It was a lot of hard work. I had to sit down and really grind and stare at my and understand like how to work really hard. It was one of the biggest challenges I went through recently, and I'm really happy with how it turned out. I definitely could have turned something in that I wasn't happy about, but like I turned it in and I looked at it and I was happy with what I produced, which I was really proud of.
That is awesome. And I'm sure your parents are proud of you. So it looks like we're just about out of time today. But before we go, we have a student challenge for you. So we're actually challenging you to build a multi-stage balloon rocket. It's an activity on page 30 of the Space Launch System Educator Guide. And you will actually get the opportunity to design and build a multi-stage balloon-powered rocket to demonstrate how rockets can actually achieve greater distances using the technology of staging. So you can see the link there to the activity in the chat window, and that's going to actually take you to the NextGen site so that you can actually begin completing your amazing spacecraft. And we actually hope that you will share your work on this activity with us here at #NextGenSTEM. Two more things before we wrap it up today. I want to say thank you so much to Dominic Lundy for coming on our show today. It was great talking with you and learning more about the great work that you do. Lastly, join us for our next STEM Stars on November 4th at 2 p.m. Eastern, where we're actually going to learn more about large vehicle trajectories. How cool is that? Thank you all for attending today. Please don't forget to subscribe, and we will definitely see you soon. Take care, be safe out there, and have a great day. Take care.